When you open a carbon footprint calculator for the first time, you're usually doing so because you want an answer. You want to know your number. How much carbon dioxide are you responsible for? What's your impact? It feels like a simple question. And so you answer the questions. You tell the calculator how far you drive, whether you eat meat, how much you fly. You hit submit. The calculator thinks for a moment, and then it tells you 12 tons of carbon dioxide equivalent per year. 12 tons. You're not entirely sure what that means, but at least now you have a number. You bookmark the calculator and go about your day. A few weeks later, you come across a different calculator. Maybe it's recommended by a friend or featured in an article you're reading. This one looks more detailed. It asks about your electricity bill, not just whether you have solar panels. It wants to know about your shopping habits. You answer the questions as carefully as you can, trying to be consistent with what you told the first calculator. You submit. This time the number is 8 tons. 8 tons, not 12.8. You're confused. Did you make a mistake? Did you remember your driving distance incorrectly? You go back and check. No, you entered the same information, but the number is 30% lower. So you try a third calculator. This one is simpler, faster. It doesn't ask as many questions. It gives you a number quickly, 18 tons. Now you're not just confused, you're frustrated. 3 calculators, 3 wildly different answers, 8, 12, 18. The range is enormous. One of them has to be wrong, surely. Or maybe all of them are wrong. Maybe the whole exercise is pointless. This frustration is common. It's so common that it's become one of the main barriers to people engaging with carbon footprinting at all. If the tools can't agree, why should anyone trust them? But here's the thing. The tools aren't broken. And in most cases, none of them are wrong. They're just measuring different things. Or more accurately, they're estimating different things in different ways. And to understand why that is, we need to take a step back and ask a more fundamental question. What exactly is a carbon footprint calculator trying to do? Most people, when they first use a carbon calculator, approach it with a particular mental model. They think of it like a scale. You step on a scale, and it tells you your weight. The scale measures a physical property of your body at that moment in time. It's a direct measurement. If you step on 3 different scales, and they're all properly calibrated, they should give you 3 very similar numbers. If they don't, at least one of the scales is faulty. That's the expectation. A calculator should calculate. It should give you the truth. And if 2 calculators give different answers to the same question, at least one of them must be making an error. But a carbon footprint calculator doesn't work like a scale. It works more like a weather forecast. When a meteorologist predicts the path of a hurricane, they're not measuring where the hurricane will go. They're running a simulation. They take current data, feed it into a model, and the model projects a likely path. But the model is built on assumptions. It has to simplify the atmosphere into something a computer can process. Different weather models make different assumptions about air pressure, ocean temperature, wind patterns. And so, very often, the European weather model and the American weather model will predict slightly different paths for the same storm. That doesn't mean one model is broken. It means they're using different methods to approximate something that's fundamentally uncertain. Carbon calculators work the same way. They're not measuring your footprint, they're estimating it. And estimation always involves choices. Choices about what to include, what to exclude, how to handle uncertainty, and how to translate your life into numbers. Let's think about what it would actually take to measure your carbon footprint directly. Truly measure it. You'd need to track every single emission connected to your existence. Not just the exhaust from your car, but the emissions from the factory that built your car. The emissions from mining the metals that went into that factory's machines. The emissions from the truck that delivered the metals to the factory. The emissions from refining the fuel that powered the truck. You'd need to know the exact carbon intensity of the electricity grid at the exact moment you turned on your kettle this morning. You'd need to trace the origins of every item of food you ate, every piece of clothing you bought, every service you paid for. And you'd need to know not just where those things came from, but how they were made, transported, and eventually disposed of. This is obviously impossible. The data doesn't exist. Even if you wanted to track it, you couldn't. Most of the emissions connected to your life happen far away, in supply chains you'll never see using processes you'll never know about. So, calculators estimate. They use averages. They use proxies. They make assumptions. And this is where the differences begin. The single biggest reason calculators give different results isn't about data quality or mathematical errors. It's about something more fundamental: the system boundary. The system boundary is the invisible line that defines what counts as your emissions and what doesn't. And different calculators draw that line in different places. Let's start with geography. Imagine you live in the United Kingdom and you buy a television. That television was manufactured in China. It was assembled in a factory that runs on electricity from a coal-fired power plant. The plastic casing was made from oil refined in the Middle East. The screen was made with rare earth minerals mined in Africa. All of these processes created emissions. Quite a lot of them, in fact. Manufacturing a television might generate several hundred kilograms of carbon dioxide equivalent. Now the question, whose emissions are those? One way to answer this is to say they belong to China, because that's where the factory is. That's where the smoke came out of the chimney. This is called production-based accounting. It's the method most governments use when they report national emissions to the United Nations. It counts emissions where they physically occur. But there's another way to answer the question. You could say those emissions belong to you because you're the one who created the demand for the television. If you hadn't bought it, it wouldn't have been made. This is called consumption-based accounting. It assigns emissions to the end user, not the producer. Both methods are defensible. Both are used, but they give radically different results. If you live in a wealthy country that imports a lot of goods, a consumption-based calculator will give you a much higher footprint than a production-based one. In the UK, for example, consumption-based emissions are roughly 40% higher than production-based emissions. That's an enormous difference. And it's not because one method is wrong, it's because they're measuring different things. Some calculators use production-based boundaries. Some use consumption-based boundaries. Many don't tell you which they're using, and this alone can account for a huge portion of the variation you see between tools. But geography isn't the only boundary issue. There's also the question of allocation. How do you divide emissions between people? Let's say you live with 3 other people. You share a house. You share a car. You share the heating bill. The house uses gas for heating, and over the course of a year, that gas creates 2 tons of carbon dioxide. Whose emissions are those? The simplest approach is to divide by the number of people. 2 tons divided by 4 people equals half a ton each. This is what most calculators do. It's called per capita allocation. It's simple, it's fair, and it's easy to program. But is it accurate? What if one person works from home and keeps the heating on all day while the others are out? What if one person lives in a larger bedroom? You could argue that the person who uses more heating should be assigned more emissions. Some calculators try to do this. They ask detailed questions about behavior. They allocate emissions based on usage rather than headcount. Neither method is wrong, but if calculator A divides household emissions equally and calculator B allocates them based on usage, the results for any individual person could differ by 50% or more. The same problem applies to cars. If your family owns a car and 4 people use it occasionally, does each person get 25% of the car's emissions? Or does the person who drives most often get the majority? Some calculators assign vehicle emissions to the primary driver. Others split them evenly. Again, defensible choices, different results. And then there's the question of time. When do emissions count? Let's say you buy a new car this year. Manufacturing that car created a large amount of emissions. The steel had to be smelted, the aluminum had to be refined, the plastics had to be molded. All of this required energy, and most of that energy came from fossil fuels. Let's say the total manufacturing footprint of your car is 10 tons of carbon dioxide equivalent. Does that 10 tons get added to your footprint this year, the year you bought the car, or does it get spread out over the lifetime of the car? If the car lasts 10 years, maybe the manufacturing footprint should be amortized 1 ton per year for 10 years. Both approaches exist. Some calculators add the full manufacturing impact in the year of purchase. Others amortize it. And many simple calculators ignore manufacturing entirely and only count the emissions from burning fuel. If you're comparing a calculator that ignores manufacturing, a calculator that counts it all at once, and a calculator that amortizes it, you could easily see a 3-fold difference in results for someone who bought a car recently. The same issue applies to housing. If you buy a newly built house, the construction process created emissions. Concrete production alone is hugely carbon intensive. Does that construction footprint belong to you? Does it get spread over 50 years? Does it belong to the developer who built it? There's no universally agreed answer. Different calculators handle it differently. These system boundary choices, where to draw the line geographically, how to allocate shared emissions, how to handle time, these aren't bugs. They're fundamental design decisions, and they matter more than almost anything else. Now let's talk about methodology, how calculators actually turn your inputs into numbers. There are three main approaches, and they produce very different results. The first approach is called activity-based modeling. This is the physicist's method. You tell the calculator exactly what you did, the activity, and the calculator applies a conversion factor to turn that activity into emissions. For example, you burned 10 gallons of petrol. Petrol has a known carbon content. When you burn 1 gallon of petrol, it releases a predictable amount of carbon dioxide, about 8.9 kilograms in fact. So 10 gallons equals 89 kilograms of carbon dioxide. The maths is straightforward. Activity times factor equals emissions. This works well for things like fuel and electricity. If you know how much you used, the calculator can give you an accurate answer, but it falls apart for complex goods. How do you calculate the footprint of a laptop? You can't just weigh it. The emissions didn't come from the weight of the laptop. They came from mining the materials, refining them, manufacturing the components, assembling the device, and shipping it to you. All of those steps happened in different places, using different energy sources, with different efficiencies. There's no simple factor you can apply. The second approach is called spend-based modeling. This is the economist's method. Instead of asking what you did, it asks what you spent. You spent $50 on petrol. The calculator looks up a database that says, on average, for every dollar spent in the refined petroleum sector, a certain amount of carbon dioxide is emitted across the entire supply chain. It applies that factor to your spending. $50 times the emissions intensity of the sector equals your footprint. This is much easier for users. You don't need to know how many kilowatt hours of electricity you used. You just need to know what you spent. And it works for everything: services, goods, insurance, banking. Everything has a price, and every sector has an emissions intensity. But spend-based models have a big weakness: price fluctuation. Imagine petrol prices double overnight because of a geopolitical crisis. You're still buying the same amount of fuel. You're still emitting the same amount of carbon. But now you're spending twice as much money. A spend-based calculator would conclude that your footprint has doubled, which is clearly wrong. Or imagine you buy a vintage leather jacket from a charity shop for $50. Then imagine you buy a brand new fast fashion jacket, also for $50. A spend-based calculator treats both purchases identically because they cost the same. But the new jacket required manufacturing, fabric production, dyeing, sewing, shipping. The vintage jacket required none of that. Its manufacturing emissions happened decades ago. The footprints are completely different, but a spend-based model can't see that. Because of these limitations, most modern calculators use a hybrid approach. They use activity-based methods for things you can measure directly, like energy and transport, and they use spend-based methods for everything else, like consumer goods and services. This is generally considered the best compromise between accuracy and usability. But here's the problem. A purely activity-based calculator and a purely spend-based calculator, given the same user, will often produce results that differ by 30 to 40%. Spend-based models tend to overestimate because they rely on industry-wide averages that include inefficient producers. If you happen to buy from efficient producers, the model has no way to know that. So the methodology choice, activity-based, spend-based, or hybrid, creates another layer of variation. Then there are emissions factors themselves. An emissions factor is the number that converts an activity into emissions. It's the exchange rate between liters of fuel and kilograms of carbon dioxide, between kilograms of beef and kilograms of methane, between kilowatt hours of electricity and grams of carbon dioxide. Every calculator relies on a database of these factors, but not all databases are the same. Let's take electricity as an example. Electricity doesn't have a single carbon footprint. It depends entirely on how the electricity was generated. Electricity from a coal plant has a high footprint. Electricity from a wind turbine has almost none. So when a calculator asks you how much electricity you used, it also needs to know where you got it from. Some calculators use a global average. They assume all electricity is the same. This is obviously inaccurate, but it's simple. Others use national averages. If you tell the calculator you live in France, it uses the French grid factor, which is low because France relies heavily on nuclear power. If you live in Australia, it uses the Australian factor, which is higher because Australia still burns a lot of coal. But even national averages can be misleading. Australia is a big country with different grids in different states. Tasmania's electricity comes mostly from hydropower. It's very clean. Victoria's electricity comes mostly from brown coal. It's very dirty. If you live in Tasmania and the calculator uses the Australian national average, your footprint will be vastly overestimated. If you live in Victoria and the calculator uses the same average, your footprint will be underestimated. The best calculators ask for your postcode or your state and use regional grid factors, but many don't, and this creates variation. The same problem exists for food. Let's say you eat beef. The calculator needs an emissions factor for beef, but beef doesn't have a single footprint. It depends on how the cow was raised. Grass-fed cattle in the UK have a lower footprint than grain-fed cattle in feedlots in the United States, which in turn have a much lower footprint than cattle raised on land that was recently deforested in the Amazon. If deforestation is included in the factor, the number could be 4 times higher than if it's not. Some calculators use global averages for food, others use national averages, a few use regional or production method-specific factors, and many calculators don't tell you which factors they're using. They just give you a number. There's also the problem of data age. Emissions factors change over time. Electricity grids get cleaner as coal plants are retired and renewables are added. Agricultural practices improve. Supply chains become more efficient. A calculator that uses data from 2015 will give very different results from one that uses data from 2024. But some calculators, especially free ones built by well-meaning volunteers or advocacy groups, are never updated. They become what researchers call zombie calculators. They're still online, still being used, but their data is years out of date. This matters more than you might think. In some countries, the carbon intensity of the electricity grid has dropped by 50% or more in the last decade. If a calculator doesn't update its factors, it's punishing users for emissions that are no longer happening. Now let's look at specific categories where variation is especially high. Flights are the most dramatic example. When you fly, the plane burns jet fuel, and that fuel releases carbon dioxide. That part is straightforward, but aeroplanes also release other things. Nitrogen oxides, water vapor. At high altitudes, these emissions have a warming effect that goes beyond the direct effect of carbon dioxide. Water vapor forms contrails, thin clouds that trap heat. Nitrogen oxides interact with the atmosphere in complex ways. Scientists call this the radiative forcing effect, and there's a debate about how to account for it. Some calculators ignore it entirely. They only count the carbon dioxide from burning fuel. Others multiply the carbon dioxide by a factor to represent the additional warming. The UK government recommends a multiplier of 1.9. Some academic calculators use 2.7. A few use 3. The same flight from London to New York could be calculated as 1 ton of carbon dioxide equivalent, or it could be calculated as 3 tons, depending on which multiplier the calculator uses. That's a threefold difference from a single methodological choice. And it gets worse. Even the basic fuel burn calculation isn't standardized. Does the calculator assume you're flying economy or business class? Business class passengers take up more space, so some calculators assign them a larger share of the plane's emissions. Does the calculator account for how full the flight was? A half-empty plane emits the same total amount of carbon dioxide, but that gets divided among fewer passengers. Most simple calculators just ask for departure and destination and apply an average. More sophisticated calculators ask for cabin class and try to estimate load factors. The results can differ by 50% or more. Electricity is another category with high variation, and we've already touched on why. The carbon intensity of electricity varies enormously by location and by time. A calculator that uses a national average versus one that uses a regional factor versus one that uses a time of day factor could produce vastly different results for the same household. And then there's the question of renewable energy. If you have solar panels on your roof, do they reduce your footprint? The obvious answer is yes, but by how much? If you generate more electricity than you use, the excess goes into the grid. Someone else uses it. Should you get credit for that? Some calculators give you full credit. Others don't count exported electricity. Others give you partial credit based on what the grid would have used instead. None of these approaches is obviously wrong, but they create variation. Food is perhaps the most complex category of all. The emissions from food depend on what you eat, but also on how it was produced, where it came from, and how it was transported. A tomato grown in a heated greenhouse in winter has a much higher footprint than a tomato grown outdoors in summer. Beef has a high footprint, but not all beef is equal. Chicken has a lower footprint, but it still varies based on feed type and farming practices. Some calculators ask very detailed questions. They want to know how many grams of beef, chicken, pork, and fish you eat per week. They want to know whether you buy organic, whether you buy local. Others just ask a single question. Are you vegetarian, vegan, or a meat eater? The difference in granularity produces huge variation in results. And then there's the question of land use change. If a forest was cleared to create a cattle ranch, who's responsible for the emissions from that deforestation? The farmer? The consumer who buys the beef? Should those emissions be included in the per kilogram factor for beef? Some emissions factors include land use change, others don't. If the factor includes it, beef from recently deforested land in the Amazon could have a footprint 10 times higher than beef from established pasture in Europe. But most calculators don't tell you whether their factors include land use change. You just get a number for beef, and that number could vary by an order of magnitude depending on hidden assumptions. Consumer goods are similarly opaque. The footprint of a smartphone, a pair of jeans, a sofa, a book, these are all estimated using complex models that trace supply chains backward through multiple layers of production. The uncertainty is enormous, and most calculators either ignore consumer goods entirely or use very rough, spend-based estimates that treat all spending in a category as identical. Now let's talk about indirect emissions, also known as Scope 3 emissions. Direct emissions are the ones you cause personally. You burn petrol in your car. That's direct. Indirect emissions are the ones that happen somewhere else in the chain. The emissions from extracting the oil that became your petrol. The emissions from refining it. The emissions from transporting it to the petrol station. Some calculators include these upstream emissions, others don't. Including them typically adds 20 to 30% to fuel-related footprints. It's called well-to-wheel accounting as opposed to tank-to-wheel. Both are defensible, but they give different answers. And then there's the even murkier question of shared infrastructure. Every citizen of a country benefits from public services: roads, schools, hospitals, the military, the civil service. All of these institutions emit carbon. Should those emissions be divided among the population and added to individual footprints? Some calculators say yes. They add a baseline to everyone's footprint to represent their share of public services. This baseline might be 2 or 3 tons of carbon dioxide equivalent per person. Other calculators start at 0. They only count personal consumption. Neither approach is wrong, but the difference is substantial. If calculator A starts everyone at 3 tons and calculator B starts everyone at 0, that's an automatic 3-ton gap before you've answered a single question. There's also the issue of services that don't fit neatly into categories. Banking, insurance, healthcare, education. These are all part of your life. They all have footprints, but they're hard to measure. Activity-based calculators often ignore them. Spend-based calculators include them, but with high uncertainty. This creates another source of variation. Finally, let's talk about user input. Even if two calculators used identical methodologies, identical emissions factors, and identical boundaries, they could still produce different results because users don't know their own behavior as well as they think they do. When a calculator asks how many miles you drive per year, most people guess, and most people guess low. This isn't dishonesty, it's optimism bias. We tend to think of ourselves as slightly better than average. I drive a normal amount, we think. But normal is a slippery concept. Some calculators ask for estimates. Others ask you to upload bills or bank statements. Calculators that force you to confront actual data generally produce higher footprints because the data reveals the truth. You thought you drove 10,000 miles a year. Your fuel receipts show 15,000. Interface design also matters. Calculators with sliders encourage you to slide toward the middle, toward average. Calculators with text boxes allow for more variation. Calculators with drop-down menus constrain your choices, which reduces variation but also reduces accuracy. And some calculators pre-fill answers with defaults. If you skip a question, the calculator assumes an average value, but averages don't describe anyone. If you skip the flight question and the calculator assumes you took the average number of flights for someone in your country, your result could be wildly wrong, but you might not even notice. You see a number, you assume it's accurate, and you move on. So, after all of this, what are we left with? 3 calculators, 3 different numbers. 8 tons, 12 tons, 18 tons, and now, hopefully, you can see why. It's not that one calculator is broken, it's that they're built on different foundations. One might use production-based accounting, national average emissions factors, and activity-based methods for transport, but spend-based methods for goods. Another might use consumption-based accounting, regional emissions factors, and hybrid methods throughout. A third might include radiative forcing for flights, land use change for food, and upstream emissions for fuel. Each of these choices is defensible. Each reflects a trade-off between accuracy, usability, scope, and simplicity. There is no perfect calculator because there is no perfect way to draw the boundaries of responsibility. This doesn't mean the tools are useless. It means they need to be understood for what they are: models, not measurements; estimates, not absolutes. So how should you use them? First, don't compare across calculators. If you want to track changes over time, pick one calculator and stick with it. The absolute number might be uncertain, but the change, the delta, is real. If you make an effort to reduce your footprint and the number drops, that means something, even if the number itself was always an approximation. Second, look for transparency. A good calculator tells you what methods it's using, what data sources it relies on, and when it was last updated. If a calculator doesn't have a methodology page, treat it with skepticism. If it hasn't been updated in several years, find a different one. Third, focus on magnitude, not precision. It doesn't matter whether your flight was 1.5 tons or 1.9 tons. What matters is that it was enormous compared to your daily electricity use. Calculators are compasses. They tell you which direction to go. They're not GPS coordinates. They don't tell you your exact position. And finally, remember that variation is not the same as uselessness. Weather forecasts are uncertain. Different models give different predictions. But that doesn't mean we ignore weather forecasts. We use them knowing they're imperfect because they're still better than guessing. Carbon calculators are the same. They're imperfect. They disagree, but they still give you information you didn't have before. They still help you see the shape of your impact, even if they can't tell you the exact size. The real question isn't which calculator is right. It's what you do with the information once you have it. If you found this episode useful, feel free to share it with someone who might appreciate it. You can subscribe wherever you listen to podcasts if you'd like to hear more. This episode was produced by EDV Group. Thanks for listening.